Would you like to go first?
Yes.
With the Laura being the brave one. And you may, same as on the smartphones, you probably can expand, zoom in if needed.
Okay. So I'm looking at the effects of an electric field on a perovskite solar cell architecture with a hole transport material and an electron transport material. Oops, what did I do? So this is the model that I'm looking at, and I made a legend. I haven't labeled it yet, but I mean it's I guess from left to right, it is cesium, lead, bromine, titanium, oxygen, nitrogen, carbon, and hydrogen. So if you take the three-dimensional orbitals, the cone-sham orbitals anyway, and you integrate out the x and y dimensions, then you're left with only the occupations in terms of the z dimension. That's what this graph is showing. And then I kind of, I threw these lines in here just to show whether or not it's localized on the perovskite or the HTM or the ETM. The whole transport material is this one on the left, by the way, and the electron transport material is the one on the right. So when we get down to this graph, I guess I'm not sure if the way that I think that it should be interpreted is the right way that it should be interpreted. Because we're making a dipole approximation with this, right? So there has to be some kind of dipole.
I may have forgotten what we did 3 days ago, but let me probably come to a cycle and ask once again, what was the goal? What are you looking for?
I'm not really clear on that.
But you're like, what seems novel to yourself? What seems like a challenge and missing, like gap in the knowledge that you may address through this modeling?
So, as far as I can tell, there aren't any papers out that deal with applying an electric field to, I guess, an inhomogeneous system, if that makes sense. So it's basically like a compounded system of, perovskite and titanium dioxide and spirometad. I was able to find stuff on just perovskites or just titanium dioxide, but nothing with the whole thing combined. So, I guess that we're looking at, what it's going to do to electronic configuration and electronic dynamics.
So you are addressing one applied and two methodological aspects. Applied that a lot of people describe how to create or to convert a photon into electron and hole pair, but there is a missing modeling of how both electron and hole depart from active layer. There are some words how on the electron and on the hole, but as both of them depart, there are no, right? So it's applied.
Yeah, I guess I don't see that.
Okay. Methodological, one that is maybe not super new, but still new for the community, that you are looking dynamics of charge in time, and it's not yet portion of standard packages. And second, that you look for response of these dynamics to external field, to electric field.
Yes.
At least you're posing this goal.
Yeah.
And it seems interesting, novel, and challenging. And any small step in this direction is appreciated by community. Does it brings you to friendship with yourself?
I guess.
Okay.
So I guess in my mind, I don't think that you can read absolute energies off of this diagram. The thing that I think that you could get from this is relative energies of transitions from one state to another.
Yes. You're jumping to analysis and judgment section. You're starting judging what are you doing before accumulating results. Let's like share plans. Probably you'll accumulate a few more things before. And it's okay that you're criticizing, but there will be other people happy to criticize you. This figure is very minor amount of data. It shows only 3 points, 3 values of electric field.
Right.
And it would be reasonable to accumulate data for like 100 values of electric field and plot density of states for each of them. Or if you do not, by some reason, you do not trust density of states, you may do like absorption spectra in presence of electric field.
But would the density of states change significantly?
Yes.
I mean, would the occupations change, or would
No.
the actual shape of it change?
No, the energies. So like if you go up, can you go up where you have like that one?
Yeah.
Like if you do energy and field strength, then they would move back and forth.
But I would think that they would all shift by the same amount in energy.
No.
So you'd get no real relative shift. Because you have the same amount of charge.
Wait.
Somewhere, right?
Let's criticize London on this constructively. Can you please repeat the last sentence?
I wouldn't think that the density of states would qualitatively change very much. Because in my mind, the energies of the orbitals would all just kind of shift upward by the same amount. Or approximately, at least.
So, London does claim that all energies will accumulate
whole energies.
with the same shift. Is it what you wanted to say? Can you sign under this statement?
No, I can't.
But wouldn't it also show that the gap's opening?
or closing, depending on the value of the field.
For this one with multiple lines,
Well,
is green lower or red higher?
Please enlarge this multicolor central figure, approach the screen and show what it is.
That is as zoomed as I can get, like that.
And please guide us through this line, maybe by approaching the screen.
So this is like one of the limiting cases where I figured out what the electric field would have to be to make the HOMO meet the LUMO in energy. So the blue line is no electric field, the red lines are positive electric field, and the green is negative electric field. So, yeah.
So what is positive and negative
Oh,
with respect to your system?
It's left and right, which is which. The positive electric field would be. So the electric field lines would be pointing to the left.
For positive.
Correct. I think. Right, because an electron would want to go toward the right, which is what would close the band gap there. Right?
So please approach the screen and continue guiding us through it, because there are some things. So where is HOMO?
Right, it's these ones right here.
And what are the three? So it's like triplet. It's three HOMOs. At
Yes.
no field, at positive field, and negative field, right?
Correct. Yes.
And can you show what is the offset of the energy
from HOMO to LUMO?
No. From HOMO with field and without field.
I mean, it would be like.
No. Show it there. It's really convenient.
I mean.
Okay. Yes.
Right there.
And now let's look on the HOMO minus 2.
Okay. God. So that would be right in this cluster right here.
What is the shift of energy for HOMO minus 2?
Much more drastic. I mean,
More drastic or less drastic?
are you saying between the HOMO tubes?
Yes.
Okay, that would be less drastic then.
So, and your statement that you were about to sign tells that each energy gains the same shift.
So my issue is that I don't see how this is a valid approximation for the absolute energies. That's what I can't.
What do you mean absolute energies? It's first order correction to the energy through dipole approximation. It's standard thing.
But I guess what is the dipole that we're talking about, right?
As soon as you enrich your poster with equations, you will be able to answer it.
Well, because I can see with transition dipoles.
No. Here are the static dipoles. That is what you're computing. So,
and say the HOMO, right? Because the dipole would be state dependent, right? Like there'd be a dipole for each state. I mean,
is there a marker?
I have one in my backpack.
Okay, let's. Here are a couple.
No.
If they work. So what is a dipole?
This is a dipole.
And what is the equation for the dipole?
I don't know, I guess if you call this like charge 1 and charge 2, then it would be.
Okay.
Well, I mean, depending on.
And put like D equals and this stuff. Okay. And if there are absolute values of charges, then you probably put minus in front of second term.
Right, yeah. I don't know how you want to think about that, but.
Okay, so this is for the point charges.
Right.
What if the first term includes more than one positive charges? You put. Okay, what is the, yeah, that's fine. What is the second term? Is not for point charges, but for distribution in space. Like there is a probability charge distribution in space. How does this change this equation? No, second. First term for positive ions stays the same, but electrons are distributed in space.
I guess this is just like positive or negative charge with the way that I wrote it.
Wait.
Just like.
Plus are ions, atoms, nuclei, and negative are electrons.
Right.
In your first equation, you separately treat positive and negative charge.
Okay, so.
So now let's do something. Okay. Summation.
We'll call like little. Oh wait, this is for index. I don't know, little n for electrons, I guess.
But your electrons are still point charges on your second term. What if they are distributed? Okay. Integral over space, like d over volume. Write equal and just continue so that write it once again, because you're jamming writing and do not erase. Do not erase. Then we will not see the constant sequence. So for positive charges, summation over all ions, position of ion times charge of ion. Okay, minus summation over number of electrons, and for each electron, integral over volume element, dV or dr, whatever.
Oh, yeah.
Dr. Keep it same equation times position, vector of position, times distribution of charge. Not of I. Rho is a continuous function of R.
But it'll have, you're going to have a different rho
Yes.
for each state.
Yes.
I guess is what I'm getting at there.
Okay, good. Now, how does this equation correspond to what you are showing on the diagram?
I mean, this doesn't really take into account the ions, though.
But ions do not change when you go from state to state. It's like a constant that you add or subtract, and it doesn't change anything.
Okay, no.
So what you are showing is the last term, term that on the equation that you draw, and your x axis on your figure is the same.
Yes.
And depending on the orbital, each orbital has different distribution in space, and therefore each orbital has different dipole. Therefore, your each point has different value of x projection.
Okay, so the orbital or the dipoles are formed between all of the ions and one orbital.
Mm-hmm.
Okay, I didn't get that, I guess.
Okay, and depending on which orbital we are looking at, each orbital interacts with electric field with different intensity. Each orbital gets different energy shift. Now, can you please point with your finger on some orbitals once again for discussion? HOMO again. So for HOMO, red is higher than green, right?
Yes.
Can you point on the LUMO? What is higher, red or green?
The other way around.
So not only the value, but the sign of the contribution from interaction with electric field is different for each orbit.
Yeah.
So, and this, therefore, what you were about to sign is very incorrect. So the main thing of your work is that you quantify the extent of electric field interaction with each of orbital. So each of orbital gets different shift in energy. And all observables in experiments and photovoltaics will depend on this. So it's
I guess that makes a little more sense. Yeah, I had no idea how to justify that. Then, yeah, I mean, right now I just have these.
why don't you start
wait a
from
minute,
why don't you
actually.
start from 0?
What's that?
For spectrum, why you start from 2.5, not from 0? Is there a specific reason?
No, there's not a specific
Okay, so you plan to update it.
Yeah, oh yeah. Yeah, these are just kind of rough drafts to make sure things are working. So, when I'm trying to run fast calculations with an electric field, do you think that I should use this value of an electric field for the positive and then do like the same magnitude but negative for the negative, or I mean,
Yep,
is there like
yep,
a better one to
makes
do?
sense.
I mean, I don't know, because the negative one doesn't really have any physical significance at that point. You know, I mean, there's no like reason to go with that one.
In the dipole approximation, the shifts of energy are different for each orbital, but they are linearly proportional to the strength of electric field. Therefore, we need only the slope, and then even if you do true calculations, if you slightly change or make electric field stronger or weaker, it will the shifts of dipoles will change proportionally as it is expected.
Okay.
Anything else?
No, I mean, these things that got turned sideways for whatever reason. Going from Mac to Windows.
Yeah.
But yeah, I mean, these are the same things before. And the conclusions that I did expect are out the window now. So,
Any questions to London from any of us?
So how do you know which one's a hole and which one's the electron transporter?
so I mean, I guess if it already operates, the way that you would know is that
So if you looked at the p dots, you didn't know anything else, could you tell me which one's a hole and which one's the electron?
It's a provocative
Yes.
question. He knows the answer. He just wants you to.
So if you're looking at a PDOS, then the species, I guess, that has the higher valence band edge will be your hole transport material, and the material with the lowest conduction band edge would be your electron transport material. Which it does work out that way, I guess, in this case. This is the HOMO right there, and then that's the LUMO. So I don't have the PDOS printed off yet, but
I guess I said p dots because this is kind of a p dots, even though it's
yeah,
not
kind of. But yeah, I don't know.
More questions? If no, let's thank London once again. So on Tuesday, probably each of us will give final version, because printing we will also we may have backup reservation on Friday, but posters are expected to be printed by this time, because they want a few hours or even days ahead. So will you present? Thank you. Mary? We do not have navigation. Can you tell if you see the screen? Should we move to the left or to the right? No, we just make signs with fingers. Expand, shrink, left, right.
What is a cat?
No, we do not hear it. By some way, microphone doesn't transmit things.
It was before. I think
It was before, but then it was no. Okay, let's do it anyway. Time is more precious.
Okay, so my topic is first principle study on graphing of disonium salts on silicon surface. So the disonium salt is a very powerful agent. It can be used to functionalize lots of surface, like carbon nanotube, graphene, silicon, and also some metal surface. And this kind of surface modification on the on the electron chemistry, under heat, under electrosonication. So in this study, we want to two problems. The first one, we want to figure out how this kind of surface functionalization reaction happened. The second is we want to figure out what kind of changes this functionalization will introduce to the system. So this is my model. So to figure out the chemical reaction, we use ab initio molecular dynamics. And this is my geometry optimized model. And first we want specific temperature molecular dynamics to get to sample from the trajectory. So here is my result for ab initio molecular dynamics. So the blue means the distance between carbon and silicon. Red means the distance between bromine and hydrogen. Blue is the distance between carbon and nitrogen. So in the AIMD trajectory, first we observe the breaking of the carbon-nitrogen bond. And as time goes by, we can see the formation of hydrogen bromide. And then finally, we see the attachment of the phenol ring to the silicon surface. And this AIMD is performed at a high temperature. So because of this high temperature, we can see some surface risk construction. So the next step is to quantify this kind of changes due to surface modification. So we prepare 4 atomic models. So the first one, the surface is fascinated by hydrogen, and this one, only one phenol ring is attached to the surface. Here, half of the hydrogen is replaced by the surface, is replaced by the phenol ring, and finally, all surface are functionalized by the phenol rings. So here I calculate the density of states and also absorption spectrum. So the first 3 looks similar, but for the last one, because of the phenol group is kind of bulky, so there is some pipette stacking and also some rearrangement of the surface. So we see the HOMO orbital is now occupied by the carbon. And I guess next time I'll add some data on trajectory dynamics and also emission spectrum.
Okay, that's it?
Yep.
Let's thank Kevin. Any questions?
I have a question. So here, I have a question for corresponding answer. For Dr. Killian. So when I did experiment on this surface, my question is, how do you determine the temperature for molecular dynamics? It's 2000 Kelvin, I understand it's around more than 1700 Celsius, right? For molecular dynamics, 2000 Kelvin.
Well, questions should be addressed to the author. I may not be.
Okay, so when I did experiment, so silicon surface it is exposed to the environment, then it is as silicon oxide. When it put into the vacuum, ultra high vacuum, and if we regas it, and if we apply heat, then the silicon layer, there is no silicon layer, silicon oxide layer anymore. And then around 1000 degrees Celsius, if we flash anneal, not anneal, flash anneal, like passing current through for 30 seconds or so, then we can get the structure, so reconstructed silicon. And if we go beyond that temperature, like higher, like in 1300 degrees Celsius or 1400 degrees Celsius, then the surface is damaged. Nothing at all we can see.
Okay, I've got your question. I think I've got it. So let me translate your question to the author. What is the goal of this modeling?
to capture the chemical reaction.
And what is the goal of chemical reaction? Why? Who needs this chemical reaction? What is the reason for this chemical reaction? There is nothing tricky. It's very trivial answer.
Don't we just need it for functionalization?
Yes, and as I see, there is no audio connection with Mary, but she was declaring this answer while talking to Daniel Ramirez last time. So the untreated surface of silicon has ability to create trap states, which are bad for optics and electronics. And the hydrogen passivation is good for computations and good for vacuum environment. But in industrial applications, it is chemical reactive and it will not stay long enough. And the reason is to protect surface so that silicon doesn't, each silicon atom doesn't have dangling bonds, it has some protective capping. And this capping is chemically stable.
But I guess Futima's question is,
Yes, it's. Do you accept it? Do you accept this statement about the goals of the research? So the goal is to protect surface.
Protect surface.
Protect surface.
Protect means there should not be any reconstruction.
Prevent formation of dangling bonds. Reconstruction is cool, but it exists only in vacuum. If you expose it to the air, it will oxidize and will form. It will protect naturally by forming silicon dioxide. But what if we are talking about nanostructures and we cannot make them bulky? If we do not want heavy layer of silicon dioxide, we want something much more delicate and versatile. Okay, wait. Will you accept this statement?
Yeah.
Okay. Now, what do you wanted to say?
I guess maybe Futima's question is 2000 Kelvin is not stable. It's too high for stability of silicon.
I'm not sure whether
She's concerned about high temperatures, which may be above melting of silicon or above temperature when it is
exactly melting.
becomes too reactive.
Yeah.
But again, the goal of the research is formation of protective layer, the dynamics of protection of protective layer, not the end structure. So what you're simulating is the dynamical process, how the protective layer is being deposited. Later on, upon deposition of these ligands, the sample is cooled down to like room temperature or 0 Kelvin. And then exploration of electronic structure is performed at optimized 0 Kelvin structure. So the question is the intermediate states during this elevated temperature are not stable. It's chemical reaction. And if one keeps system at this temperature, other reactions may happen. So as soon as desired reaction happened, what Jonas shows here, green line, carbon to silicon. So silicon atom on a surface forms a chemical bond with carbon. See, carbon to silicon bond stabilizes at 2 angstrom. As soon as reaction comes to this metastable state, after this one needs to cool down and perform electronic structure exploration at low temperatures. So you may have some objections about electronic structure at elevated temperatures. No, The goal is not to explore electronic structure at elevated temperatures. It's ways to form right structures.
But I think
Oh,
she's
huh?
saying at the elevated temperatures, when you anneal them, the structure changes. So by going to 2000 K or whatever, the structure goes from bulk to different, like 7-7.
For 7-7, you need to have 7x7 unit
Sure.
cells.
Whatever.
So it will not happen.
Whatever the construction is, I think that's what she was saying.
My
But-
question,
But saying that it is 2000 K doesn't necessarily mean that it's 2000 K, correct? Because we are using classical approximation to figure out the temperature. So although it might say 2000 K, if you actually compute like distribution function and all that crap, then it might not be actually 2000 Kelvin. Is that also a correct statement?
Yes, it's correct, but
there is no way to determine that.
wait, no. There are different regimes and different time scales. So the reconstruction Fatima is warning and caring about happens on macroscopic times, like seconds or milliseconds. These chemical reactions happen on the time ranges of nanoseconds, of like 10, 100 femtoseconds. So it is this specific species that Yulun is depositing to the surface is extremely reactive. So it will react and protect surface much quicker than any formation of this 7x7 reconstruction. And elevated temperature here, I don't know, we need to, Yulun is the best person to ask because I do not know all the details. But the reaction on experiment may happen even at lower temperatures, at room temperatures. So the elevated temperatures in the modeling is utilized since human patience is limited and computer resources. So if one would have sufficient patience and run dynamics for long enough time, it will happen at room temperature as well, before any reconstruction. So it's the main advantage and finding of this work that one starts with chemically intact precursor, and this precursor, while approaching silicon surface, decomposes on fragments, and one fragment attaches to the surface, another fragment departs to exhaust. And this is the healthy process as it creates a protected surface that is ready for optical and electronic applications.
Okay, so
Please.
so this is unit cell, right? And it has big one, right? Or it is,
Please wait. Unit cell and simulation cell are different concepts. If you do not have ligands deposited on the surface, the unit cell is extremely small. It's like 12 atoms. Here, again, details should be provided by author. I may make mistakes, so please correct me if I'm wrong. To my understanding, the unit cell is replicated substantial number of times, not for 7x7, but maybe it's like 4x6 unit cells, or like 3x3, and then for this, I mean in X and Y for the surface. And then for this surface, one adds the adsorbate molecule, and from this instant, since we, in each experiment, each numerical experiment, we specify surface concentration. Like if there are, in the middle, there are 4 surfaces with 0 deposition, with about 1/8 of a monolayer, with about 1/2 of a monolayer, and with 100% of a monolayer. I just don't see from here. right? So this is the unit. It's a simulation cell, but in the sense of surface chemistry, it also serves as a unit cell, because with specific concentration. So it was just a little disclaimer to be careful about the unit cell.
Simulations.
Yeah. And now please continue asking your question.
Okay, I'm going back to the previous question again. So, I think it's a good idea to determine temperature for molecular dynamics.
What do you mean determine?
Like
To specific, you suggest to perform several simulations with different initial temperature?
So I think it's good to check the literature and see at what temperature silicon surface does not destroy, and use that temperature for molecular dynamics. That's what I think.
That's a good idea.
I don't
That's a
know.
good idea. But
If you correlate with the experiment, I understand that.
no, it's a really good statement, and highly likely the reviewer will ask the same question. So we need to design how to address this question. But there is another aspect. Like if you would try to do the same numerical experiment, you'll see that time from launch of your reaction until you happen something chemically happening is non-linear, drastically depends on temperature. And if you put realistic temperatures, you may need to run your simulation for like 100 picoseconds, which is impossible for ab initio molecular dynamics. And this is a trick that we practice. So we increase temperature to slightly unrealistic values, but then we bring the delay before reaction launches to limits that we can afford on the simulation. So your question is correct, and it needs to be addressed, at least as an intellectual verbal comment. But very often it cannot be addressed by actual simulations, because it will take too long, longer than we have at our disposal.
So is there any literature on experiment about this?
A week ago, Yoon started his presentation with showing some.
I think that was also simulation.
It was not simulation, it was experiment. There are some simulations about decomposition, about temperature activated desorption of the ligands. But for adsorption, it's rather innovative. So it's cool stuff that maybe no one did before.
So a pretty comment when your poster's divided by like half, so like the actual size. I'm not sure if in your computational details, if that model is going to actually give any worthwhile meaning. So it might be good to like cut off the top and bottom, because then you can actually see how like the molecule in space, because realistically, although you say it's fixed, you can say we have 4 more layers or 10 more layers and they're all fixed. But then that way you can actually see it versus like seeing a few dots. And then it might be also similar when you go to your results, because if you divide like the height and width by 2, the half monolayer, eighth monolayer, 1 monolayer, and 0, it might also be too small to recognize anything. But you can always say when you're presenting, oh, sorry for this small size, if you want. But that's just a comment for like making it pretty. Yeah, I like how you did results like A, B, and C for your ab initio molecular dynamics. How you like cut it so that you can actually see what's going on.
Yep. Thank you.
Or I think Mary might have a question, but we can't hear her, so maybe she should write her question down and put it in front of the screen.
Good idea. Very innovative. It's a discovery. I agree with poster organization. Don't worry, be happy.
I think she was saying the picture stuff.
Symbol of smile. Okay, thank you once again. And we have presentation number 3 in today's program. And the author may recognize herself. So I think you can operate it the same as smartphones for enlarging. And if you present it near the poster, probably it will be the best thing.
I have presented this research so many times. The same audience. So the photoluminescence calculation is not 100% complete yet, but we will try to show something. So the motivation of this research is we know periodic structure depends on the momentum sampling along the growth direction. So we want to study some electronic properties of 2 silicon nanowires with the momentum sampling. Here we consider 4 key points. So as you can see, this is the band structure of 2 silicon nanowires. We are considering silicon 001 and 111. So since we are considering more than 1 K points, here, as you can see on the right panel, rightmost panel here, there are 2 kinds of transitions, momentum restricted and momentum unrestricted. If electron or hole, I mean charge carrier travels from 1 K point to another K point, then it is momentum restricted. And if a charge carrier transfer from follow the path from the same K point, then it is momentum restricted. So here, do I need to talk about the equations?
Of course, and we all need to write down corrections to the equations to suggest what is good or what is wrong with them.
So for calculating the on-the-fly electron to lattice coupling, we use this. This one is main equation, 1 electron quantum equation, and this is the solution of these equations. You can see. Once we have these equations, so when the model is exposed to the light pulse, then electron travels from valence band to conduction band to the excited state. When the electron comes back to the band edge, then electron coupled with the nuclear motion. Then we and using this equation, we can calculate the coupling between electron and nuclear motion. This is the equation for calculating non-adiabatic couplings between electron and nuclear degrees of freedom. Once we have these coupling equations, we can get autocorrelation function from that equation, and then rates of transitions. So using these rates of transitions, we can calculate the rate field tensor. And using that rate field tensor, we can get the density matrix, where the is there any pointer here?
Oh, your laser. Okay.
So this term is the energy dissipation term. This one. Then we can calculate the non-equilibrium charge distribution as a function of energy and time. And the expectation value of energy carrier is we can get the expectation value of energy carrier using this equation, and then we assume a single exponential function to fit this energy dissipation rate, and the rate of relaxation of carrier is here, this equation. This is the expectation value. And finally, you can calculate the photoluminescence. Probably this is not the right one. There should be one oscillator term on the right side. This is the overall methodology. Now I'm going to talk how.
Can I ask you a question about
Sure.
the equation? So from the last equation,
This one?
yeah, why is there minus epsilon? Epsilon.
Minus epsilon. These first two terms is energy difference between two states. Right?
Yeah.
And this is the energy of LOMO, right? LOMO or HOMO, this one.
No, it just says epsilon. So that should just be energy.
Yeah, this is energy. So energy. I think this is the energy energy difference between HOMO and LOMO, right? This epsilon.
So is this making this graph? The
Yes.
PL one?
This is the energy difference between HOMO and LOMO, and these I and J, they are orbitals. What is
So
the question?
this is like plotting with a Gaussian distribution. So it's
You mean this
centered
one?
at your
Centered at energy difference
and
for each pair of orbitals.
Okay.
Right? It is what you wanted to say.
Yeah, but there is a.
So, question of Levi was very simple. What is epsilon without indices?
The energy difference between HOMO and LOMO band.
No. It is a argument. Argument not in logical sense, but in mathematical. So your spectrum depends on either wavelengths or energy, which ranges from whatever 0 to whatever you need. So it is the spacing of all possible values of energy, independent on which system you have. So in the code, it's like energy grid variable.
So then should you plot that using a conical like a delta symbol? Because typically when you see a delta symbol, the argument inside, wherever that is equal to the energy, that is where it's maximum, and everywhere else is 0. If you say the line width is infinitesimally small, right? Is that correct?
Yeah.
If you use the conical delta, or like
Dirac.
the Dirac delta, do you need that third term? Because I thought
Yes.
that
Yes. If you do not include the third term, then we will not have continuous function. The answer is function of epsilon.
Wouldn't you need another sum? Then just to go through all the, or to sum through all energies.
I think that's
But she has
implicit in the
summation of
sign.
j less than homo, summation of I bigger than luma. Right?
Mhm.
So this one was not a trap question. It was fair attempt to understand what is expressed.
Yes.
Okay, please continue. Sorry for interrupting.
So here I wanted to show how the states are arranged for calculation for calculating dynamics, relaxation rates, and photoluminescence. So this is the loom of the key point 1, and then the next one is loom for key point 2, and for next one loom for key point 3, then key point 4, then it starts from loom plus 1 for key point 1. That's how the states are arranged. And this one we need for these calculations, all of these dynamics calculations, not for the assumption. Here we can see the absorption spectrum in the visible light planes. There are two columns here. This is for silicon 100 model, and this is for 111 model.
So before we go to results, are there more questions about equations? So it is work in development, and any criticism, suggestions, if any equations seem suspicious, please, Fatima will not mind if you criticize or suggest that something has potential for improvement.
So if we go back to that equation, why don't you put momentum energy, like
This one?
epsilon E I comma K? Because wouldn't you use the momentum energy, like for each momentum you plug this in?
This is a good question. For photoluminescence, I think we are considering only direct transition.
Yes, but don't you have direct transitions between K points that are not 0? So if you include
so I
K
think I need
points
to add
non-zero,
momentum.
then wouldn't you need to also look at all?
For calculating this, I didn't use momentum.
But
So
when
there
you
is a
showed that video, it had different momentums. and
There is
didn't you-
the dynamics figure, like how electron and hole come back to the appearances.
Yes, but don't you integrate that over all time? to
Can you
get
point with the laser which equation you are discussing?
the same one, P
He's
epsilon?
asking that don't we need to add momentum in this equation for photoluminescence?
It's everything is good, nothing is dangerous, but it's a lot of meticulous, dirty work to complete.
So what you can just say in like the explanation, all energies are the same momentum.
No. I'll probably approach and show. So we need to be very meticulous with definitions and meaning of the indices. Somehow by jumping from one equation to another did change. So, did you present this table? Everyone accepted it? No one criticized? By the way, if you find any misspelling, if there is a grammar correction also, please do like I'm not sure if it is resultant, it's resulting. So here, this is a dictionary. It is really, from my point of view, this table is a major discovery Fatima did. It was major technical difficulty, and without this table, everything doesn't have sense. So it's a core of the work. So this table shows conversion of pair of indices. So orbital index, and we need to put some letter here. Maybe I or J. See, there is ambiguity, and we need to set up definitions and follow them. So one index for number of orbital, number of band in the language of ASP. Another index for number of K point. And then these two indices are merged into unified index of all states. Maybe one may use Latin letters here and Greek letters here, like alpha, beta, or whatever, like mu. So, do you follow? This is intentional for you.
I think so.
So here, here I would put. Well, we need to redesign or check notations, but there are two indices. One index of band, not orbital, band. Another index of K vector. And then these two indices are unified in a super index, which we may use Greek or uppercase I already reserved to ions. So in the equation that Levi is asking, the indexes of these energies must be super indices that include K.
But then you
Greek,
can't
mu
say
and nu.
I, like J less than homo, I greater than luma. Because then,
Yes, this is also needs to be updated.
yeah.
Maybe J belongs to valence band, I belongs to conduction band. Okay? Whatever we mean under this. Make sense?
Yeah.
Okay.
Okay, so in order to answer your questions, I would say momentum is already taken care of. Because if I select, suppose 65 here, initial, this is 65, so it is LOMO plus 17 for K point for gamma band. If I select 66, then LOMO plus 17 for K.1.
Yes, but we
So,
already know that
that's-
oscillator strength for non-conserving momentum is 0.
What is it? Can you please repeat?
So if you go from an excited state, which K point n,
Mhm.
and ground state to K point not equal to n, there won't be a transition. It's forbidden.
Yeah, so see here I selected LOMO plus 17, HOMO minus 17.
Yes,
At the
which
same K point, at the
But-
same K point.
as you relax in energy,
Mhm.
you do not impose that the K point has to stay the same. So the K point can vary, right? So if your K point varies in time, then you need to have a way to say, look at only K points that have the same in the excited and ground state. If they're not equal to the same, they should be 0, which is why I
That makes sense.
asked, why don't you have K in there?
Yeah.
Thank you.
So for photoluminescence, I think we need to say that
I'm-
the K point should be same. Like K equals K prime.
Sure, yes.
So a little disclaimer. You are posing the right questions. The work is not complete. It is work in progress. And what is labeled as photoluminescence is not a photoluminescence. It is a very rough step towards photoluminescence. Very rough. And the equation that is being shown in this blue diagram does not include oscillator strengths between states. So if And one more equation should be added here for integrating this P of energy and time over T, so that the analog of an emission spectrum will depend only on energy. See, this diagram is two-dimensional, it depends on time and energy, and this one depends on energy only. So in shape, in the numerical data format, it is analogous to emission. But it is not emission because it is not weighted by the values of oscillator strengths. By placing oscillator strengths here and making a few more adjustments, some of the lines will become stronger, some will become weaker, and profile of the spectrum will change.
So it's just occupations?
Yes,
Time results?
yes, right. So the peaks will stay at the same place. It's very good to predict the position of peaks.
Would it be time integrated coefficient? Not.
The right side's time integrated, the left one's time
It's-
results.
yes, okay.
The procedure will be the same. Include oscillator strengths and then time integrated. And then the peaks on the time integrated thing will be looked differently in amplitude, but they will appear at the same transition energies. Does it address your question?
Yeah,
Okay.
but I still think there might be some misinformation or like weirdness if you don't talk about K points in whatever equation you use to get those. Because if you're talking about PL, you have to have the same K point.
Right, right.
Okay.
Therefore, the discussion here is happening.
Yes.
Therefore, his presentation is made not to brag with achievements.
Yes.
It's a suggestion to everyone. The presentation at conference have main goal to collect healthy suggestions, constructive criticism for a subsequent improvement of the papers. Therefore, it is really important that first author who is taking all things in the control comes to conference and collects the feedback. Okay, keep going. More questions about equations. Let me share, if you don't mind, let me share a couple before you go to results. So this is a question that Braden Waite was really interested about, and his colleague London could be interested as well. So in this equation, one probably needs to replace this number to number minus ik, because otherwise all orbitals will be the same. There should be something, well, potential depends on k, but also to make it k dependent, there should be explicit inclusion. Why this equation is different for different k and why it develops different orbitals and different energies for different values of k. Another comment. So the von Neumann equation here looks like it was, by the way, it's better to avoid letter k because as index of orbitals because it interferes with k for momentum. Maybe like letter m is better. And it looks like this equation is inherited from the work where transitions, with direct transitions only. It one may double check if momentum would be permitted to change if this equation is practiced. Again, we all are at the development stage. I can also make errors. So here, let me share a suggestion for this equation. So index of orbital or band index, and then index of momentum. Right? And then when we make a summation, it is always as in multiplication of matrices, the outer indices here and there coincide. The last index here and there also coincide. Right? And then the mute index, the last index of the first matrix and first index of the second matrix should also coincide. And the mute index that we use in the center is what we place in the summation. So we can put a new letter like M for band and K double prime for summation of all momentum. Just but think, discuss, consider, and maybe update the equations.
I always thought HC was higher corrections.
Hmm?
I always thought HC was higher corrections.
What is HC?
Or you had it on the equation.
H.C.
H dot C.
H dot C.
Isn't it plus constant or something?
What? Which equation?
The one that you just had shown.
Let me bring it back. Oh, Hermitian conjugation.
Yeah, I always thought it was higher corrections. But I guess.
No. Well, there is a swap of. It's a commutator in the matrix form, right? And then here you swap the order and write row F, and then the same game with indices. I, K, M, K double prime, M, K double prime, J, K prime.
Mm-hmm.
And there should be a minus between them for because of the commutator.
Yeah, that makes sense. I just never knew it. I don't think we ever actually mentioned it in the paper, or when I was writing it.
It's HC is what lazy people do. When you do not want to write many things, you just skip and write HC.
So this doesn't have to deal with the equations explicitly, but it might be more beneficial for a reader if you had a single column of your methods instead of going down and then having to jump up and then going back down. So like your method section starts at the bottom and then it jumps up.
So you want to swap motivation and a second part of methods?
Or switch initial conditions and put it up. But that's also a very minor thing. But as a reader, if I come up to you, it might, like at first glance, say, oh, you have method, and it stops, and then, oh, what is this section? Because everything else has like the title above it, but not the continuation of the method. Does that make sense? But that's like super picky, so don't really worry. Please increase font on graphs and add graph size.
No, you added
yes.
the
Those graphs are not finalized yet, so.
For LX graphs and PL graphs and Word. Okay, yeah, thank you, Mary.
Any other question?
Intro.
Intro. Bigger.
Big. Yes, okay. Okay, no question? Then I can move forward then. Okay, I think initial state selection, this section is clear. Right? Everybody, any question? No.
Yeah, if there are questions, I wouldn't call it initial state selection.
Okay.
Correct me, because you are the main author, but I would call it dictionary.
What?
Dictionary. Dictionary, translation.
Okay.
Because it translates from pair of indices for band and momentum to single index. It's not necessarily initial state. You may start with some other. You do this procedure for all states. So it's the word initial is discrepancy. When the word initial means time dependence at time equals 0. For some people. Some people may have different logical concepts, but the word initial is special.
Okay, so as Levi said, if we want to calculate photoluminescence, we need to select the same K-point states. Here, in this dynamic figure, we can see I selected the same states, but this one is different. So I need to select same states for photoluminescence calculation. And these two figures are not quite complete yet. So there is a discussion in person.
So then for 111, you said that you don't have the same momentum, right?
Oh, for this figure, yeah. For these, both of these figures, same states, same K points.
Okay, so they both have the same initial K points.
Yeah, I just show.
Okay.
I just put it here for different initial states. This one and this one not same initial states. So now I would like to talk about the relaxation rate, relaxation time. If anyone has question before that, please ask. So these two figures for relaxation times of electrons. And as we can see, these results are already published. This one, Journal of Physical Chemistry, that was published on January 23. And so that's why for Levi, that's why I was keeping this slide, because it is old result and it is published in it. I just put it there that day just for reference. And this is the result from new calculation for hole. In this article, holes are not included. Now there were some problems in calculation. Now I believe the problem is solved. And here these are the relaxation times for holes for both models. And as we can see, I didn't fit this trend yet, but we can see that if we consider direct and indirect transitions both, that is called Hall transitions here, holes relax faster than Hall relax faster for all transition compared to momentum restricted transitions. So these above data, those are for momentum restricted, and these bottom field symbols, those are for all transitions. And the same thing here, probably after fitting, I would say there are two regimes where energy gap law follow, and for the second part, I would say the inverse gap law is applicable here, the second part. But I need to fit it first. I'm hoping that I am able to complete them before Tuesday. And for any question for the relaxation times for holes? If no, then I would like to go to conclusion section. So, as like previous conclusion for electrons, I would say the same thing. For indirect transition, relaxation is always quicker because there are some additional paths. For direct transitions, mean momentum restricted transitions, relaxation is slower. And energy gap law works differently for each K point. That's all.
Okay, thanks. Any questions additional to our discussion?
Apparently increasing all fonts.
Increase all fonts.
That was Mary's suggestion.
Yeah, Mary
Yes, but-
said that.
I'm not sure. Again, do not take my opinion too seriously, but for me, fonts seem large enough because you will print it about the same size as it is on the screen right now. In conclusions, maybe, but it will be printed about this size as the size of the screen, and all visitors will approach to the distance of like 2 feet. So-
Isn't it like 4 feet by 3 feet?
Which is about this.
Yeah, 42 by 36.
So the visitors will physically approach to the distance of the handshake, and most of no one will look on it as we do right now from 30 feet away.
It's readable on here, so. Yeah. I know that you said that these are just like fillers, but when you get your stuff done, make sure you put what's on your axes.
Yeah.
I'm assuming these 4 all have the same,
Same axis. Yeah.
but yeah,
That's why I put just one so that
yeah.
you guys can understand what's the axis are.
Any other questions?
Well, thank you for reading.
I have another one. So in your motivation, you talk about PL, right? And then you also have PL over here, but as we were talking, this isn't actually PL, right?
Not yet. Yeah.
Approximate PL. So you can just put approximate for 2 PLs.
I wouldn't even say it's approximate PL.
I would say it's item.
Well, it's half of it. It's the occupations.
Yeah, but the oscillator strength are the important part of PL.
Yeah, I mean, all that's really going to happen is like those faint occupations are just going to disappear. So you can kind of envision
But
what
the
the PL would be.
ratio of the major peaks.
So then, yeah, that too.
And,
But you know where the peaks are, and then you can kind of project.
and you typically don't see, or I might be wrong, do you see 2 peaks when you look at emission from these compounds?
Mm-hmm.
You do see 2 peaks.
Emission means you mean this one?
Like if you take your carbon, your silicon nanowires,
Mhm.
and you throw it in a fluorometer, would you see 1 peak or would you
I
see
can
2?
see 2 peaks, but I'm not sure. This
No,
is
not
correct or
you, experimentally.
Oh, experimental? I didn't check.
Looks.
Because
I think it has a very high onset, and then kind of levels
Yes,
out
but-
for some.
this is 3 EV different. If you look at the energy. So I would even say that this is not PL because it's not realistic, because you only get emission.
This one, right?
e-
This one?
Either of these. You only get
Yeah.
emission typically from your lowest states. So your high states that are there for a very short time, you don't see PL from. So the states at like 4.5 and almost 5 aren't there experimentally.
It is true that they are not real photoluminescence. So I'll change the name. If I cannot calculate real ones, then this name must be changed. Okay. Any other questions?
More questions?
Is it possible to report like final momentum state? So like for your green figures, you report what your initial or what they start out as. It might be helpful to put with the final momentum. Like once it cools to the band edge, what's the expectation value for the momentum?
The final momentum is always the same because final state is determined by the band dispersion profile.
Oh, true.
So you start in different states, but you end always in the same.
It's always at the gamma or
I thought
Well,
that,
in gamma, if it is
For
direct,
gamma, it's
or
the conduction band minimum.
right?
I thought that for the whole, it does not go to k equals 0 always. There's some dispersion.
Because they are kind of degenerate. If there is
Yes.
if dispersion is minimalistic, then there is a superposition of several states.
For silicon 111, I think it's not done. For electron doesn't relax at gamma point.
Yeah, for
But for
We
silicon
can see it
100, it
Sure.
is pretty flat. It's the way that.
Mm-hmm. Yeah. For silicon 111, it's somewhere.
Good. More questions? If no, let's thank Fatima once again. So please collect your feedback to the speaker, and so you go and collect it if there were different suggestions. Sorry, I have to go talk to you all later. And symbol of cat. Stay warm. You too. You too. And I'm going to show. We're going to complete very soon. I'm going to show the. Yeah. Goodbye. Goodbye, Mary. I'm going to show the program so that you, if you're already done or about done with your posters, you may develop plans on attending or not attending some talks. So the Sunday, if you are on Sunday, Kevin Gimo is not here, but he told that he wants to make a postdoc with Henry Schaffer. Sharon Hamas Schiffer is probably the best physical chemical scientist of today, making connection between several areas, and talks are really great. Mila Slipchenko, she does fragmentation in a sense, not dynamic fragmentation, but splitting large systems on several fragments and computing the electronic structure of each, and then looking how the electronic structure of one fragment affects electronic structure of the whole system. Klaus Rudenberg, I don't know his exact age, but he's about 100 years old. So it's he's slightly younger than Schrödinger, but it's impressive. And he is Gray Cardinal of the game's software package. So the Gordon, who is author of games, and he was faculty at NDSU about 20 years ago. He is kind of former, I don't know, postdoc or student of Rudenberg, and they still work together for I don't know how many decades. For the morning on Monday, Bill Miller, he is the top scientist on Gaussian wave packets. So if you do quasi-classical analysis by wave packets, it is nice to talk to him and cite him. So maybe I need to take with me older version of Johan's poster on dynamics and hang it on the poster session as well and attract attention of him. Joe Subodnik is known for doing standard tally tests, which means doing meticulous work of justifying several methods like surface hopping and exact quantum for very similar one-dimensional potentials, and making sure that they give similar results. A lot of you know Victor Batista. If you didn't, you will enjoy. He's a cheerful person, and he was the first in the world 15 years ago who considered electron transfer at the surface of titanium dioxide. So London could be interested to listen to him and talk to him, and Victor could be interested to listen to and interact with London. So it's your primary audience. Laura Gagliardi, she's our neighbor at Minnesota, and she is the expert in actinides. So some of you worked with lantanides, but actinides have different specifics. The after lunch stuff is where you all may apply next year. So it is short talks, self-invited. So anyone can compete and with very high chance of acceptance. Timo Thunhauser is current boss of Stephanie Jensen, and they are doing metal organic frameworks. Valentin Karasev does orbital free DFT for temperatures like 10,000 Kelvin, and Arut Chakraborty does some statistical analysis of quantum dots. On Wednesday, Nipa Maitra, she is one of the developers of the TDFT, and she was like collaborator of Gross. And Hannes Johnson is the one of the, he's not developer of WASP, but he's one of the most successful users of WASP in the world. He wrote a code, or his student, who's a faculty in Texas also now, wrote a code for transition state search based on WASP. So for chemical reactions, he's also the right person to consider. Also, for your future career, you may consider talking to these people, because if time comes and they have grants accepted, they may urgently look for new personnel, and they will be hungry to hire someone. So it's network connections are helpful. And I don't know, relativistic quantum mechanics sounds interesting, but I do not recognize much of the friends. So maybe the most important part on Thursday is banquet, right? Hopefully some of you will get awards and it will be presented there. And Adrian Rothberg does applied research on quantum mechanics / molecular mechanics for big biological systems. On the last day, Herm Monkhorst, you have seen his name if you looked inside the K-points file. So he developed the procedure how WASP treats K-points. But he's not speaking, he's only the chair, because he's like 78. And Alex Zunger, he is famous for doing multi-reference, it's not just double, some advanced methods for nano systems. Okay, just share the ideas. Maybe you develop your own schedule to attend or not attend. That's it. Many thanks for coming and participating. So please plan on completing to the stage of final version by Tuesday, and we will make another round of posters presentation. So those who were not able to come today, but may look through recordings, and those who were not presenting, also try to complete.